Baikonour Cosmodrome. Constructed in 1955, it is the oldest space launch complex in use today. It is the site of some of the most important space missions ever undertaken. Sputnik, the first man-made satellite to orbit Earth, was launched from Baikonour aboard an R-7 rocket on October 4th, 1957. And on April 12th, 1961, Yuri Gagarin lifted off from Baikonour to become the first man in space. Today, Baikonour Cosmodrome continues to be a backdrop for space industry firsts. Société Européenne des Satellites of Luxembourg's Astra 1F satellite will be the first Western-owned commercial communication satellite to be placed into orbit by a Russian-built rocket, the Proton launch vehicle. Astra 1F, built by Hughes Space and Communications of El Segundo, California, is an HS-601 3-axis stabilized satellite. At launch, Astra 1F weighs 3,000 kilograms and will measure nearly 26 meters across with its solar arrays fully deployed. Once in orbit, Astra 1F will broadcast digital television and radio programming across Europe. The Proton launch vehicle is built and marketed by the joint Russian-American venture, ILS, International Launch Services, which consists of Lockheed Martin Corporation of the United States, Khrunichev State Research and Production Space Center, and the Russian Space Complex, Energia of the Russian Federation. ILS, International Launch Services, offers both the Proton and the Atlas launch vehicles to customers worldwide. Proton is the most capable commercial expendable launch vehicle in operation today. Proton can put a payload weighing 2,000 kilograms on geosynchronous orbit or a 20,900 kilogram payload into low Earth orbit. The 4-stage Proton that will lift the Astra 1F satellite is over 60 meters tall and weighs over 550,000 kilograms. The first 3 stages are propelled using unsymmetric dimethylhydrazine and nitrogen tetroxide, while the 4th stage uses kerosene and liquid oxygen.
5, 4, 3, 2, 1, пуск.
Approximately 1.6 seconds before liftoff, Stage 1 engines are ignited and the Proton roars to life. 10 seconds after liftoff, the Proton executes a roll maneuver to align its flight direction. 66 seconds after liftoff, Proton is traveling at Mach 1. The first stage is equipped with 6 gimbaled single-chamber liquid propellant rocket engines that fire for approximately 2 minutes, propelling the vehicle to an altitude of 50 kilometers. After Stage 1 separation, the 4 gimbaled single-chamber liquid propellant rocket engines of the second stage burn for just over 3.5 minutes. At this point, Stage 2 separation occurs, allowing Stage 3 to propel the vehicle to a 200-kilometer circular parking orbit. Fairing separation occurs during 3rd stage flight. After reaching parking orbit, Astra 1F is traveling above the Earth at Mach 25 speed. At 9 minutes and 49 seconds into the flight, Stage 3 separation occurs. 55 seconds after Stage 3 separation, the protective shroud of the upper stage, Block DM, is released. From the parking orbit, the Block DM will deliver Astra 1F to its target geosynchronous transfer orbit by means of 2 burns that are separated by 5.25 hours. After reaching the target orbit, the Block DM executes a 180-degree turn in preparation for spacecraft separation. 6 hours and 41 minutes after liftoff, the Block DM spins up and separates from Astra 1F. International Launch Services is proud to participate with Hughes Space and Communications and Société Européenne des Satellites in launching the Astra 1F spacecraft.
This is Proton launch control at T-minus 27 minutes and counting in the launch of the Astra 1F mission. The Proton has a long and distinguished history with a record that includes a number of significant firsts. It has also become one of the principal workhorse vehicles of the Russian space program. Development of the Proton launch vehicle began in the early 1960s under the direction of the Soviet academician V.N. Chelomey. The first launch took place in July 1965. This was a two-stage version of the vehicle that was used for a series of 4 test flights. That first version of the Proton has since been superseded by 3-stage and 4-stage models, both of which are currently in use. An improved version of the Proton M, is now in development. The Block DM 4th stage was developed independently during the 1960s as the 5th stage of the Russian manned lunar launch vehicle, the N1L3. It was originally known in Russia as the Block D, where Block is the common translation of the Russian word denoting a rocket stage, and D is the 5th letter of the Russian alphabet. The vehicle was upgraded during the 1970s to the current Block DM, or modernized version. Proton has flown well over 200 missions and has orbited the Salyut series space stations and the Mir space station modules. As a 3-stage vehicle, the Proton has become Russia's principal heavy-lift launcher. The 4-stage Proton has launched the Ikran, Raduga, and Gorizont series of geostationary communication satellites, as well as the Zond, Luna, Venera, Mars, Vega, and Phobos interplanetary exploration spacecraft. These missions produced the first samples of the lunar surface to be returned by an unmanned spacecraft and the first soft landing on the surface of Venus. All Russian geostationary and interplanetary missions are launched on Proton. Approximately 90% of all Proton launches have been of the 4-stage version. The future promises to be very busy for the Proton. Western satellite builders and operators have already signed numerous launch service contracts for Proton, with the potential to produce up to 6 commercial launches per year through the end of the century, in addition to the 8 to 10 flights that will be conducted annually for the Russian government. The upcoming International Space Station will also rely on Proton to launch its first component, the FGB bus, as well as a subsequent support module. This is Proton launch control at T-minus 25 minutes and counting. Propellant loading of the Proton began last night at T-minus 8 hours when the command was given to evacuate the last of the spacecraft and launch vehicle support personnel from the area of the launch pad. Actual propellant transfer operations began at T-minus 6 hours when the nitrogen tetroxide oxidizer and unsymmetrical dimethyl hydrazine fuel that power the first 3 stages of the Proton started to flow into the vehicle from ground storage tanks through a set of fueling connectors at the base of the vehicle. The Block DM upper stage was filled with a special grade of kerosene known as synthin before the Proton arrived at the launch pad. Liquid oxygen loading of the upper stage began simultaneously with the start of propellant transfer to the first 3 stages. The liquid oxygen is loaded through a connection from the mobile service tower. The nitrogen tetroxide and UDMH used in the first 3 stages, as well as the synthin used in the Block DM, are all liquids at room temperature and require no special thermal conditioning. Liquid oxygen, or LOX, is a cryogenic propellant that must be maintained at minus 290 degrees Fahrenheit. The LOX tank of the Block DM, however, is heavily insulated, and so very little boil-off of the propellant occurs between the time the LOX is loaded and the moment of liftoff. Propellant loading of the Proton launch vehicle in the Block DM upper stage was completed at T-minus 3 hours and 10 minutes. This is Proton launch control at T-minus 23 minutes and counting. Off the right-hand side of the live image in front of you is the Proton's mobile service tower. It's now standing 200 meters away from the Proton in its final position prior to launch. Rollback of the MST began at T-minus 1 hour and 15 minutes and was completed approximately 1/2 hour later. The MST stands more than 70 meters tall and provides a variety of services to the Proton. You will remember that liquid oxygen for the Block DM upper stage is loaded from the MST. Also, the service tower provides a temperature-regulated airflow to the Proton's payload fairing in order to maintain the Astra spacecraft's temperature within acceptable limits while the Proton sits on the pad before launch. Airflow to the spacecraft from the MST was discontinued 15 minutes prior to rollback. Thermal regulation of the Astra vanaf is now being provided by a set of radiators mounted inside the payload fairing, which circulate a heated working fluid. This liquid-based system will be disconnected and purged by dry nitrogen gas at T-minus 5 minutes. The mobile service tower also protects the Proton from high winds, although in reality winds are rarely an issue during a Proton launch. Even with the large diameter payload fairing we are using today, the Proton can lift off in winds as high as 16.5 meters per second. That's about 38 miles per hour. The MST doesn't have to be brought back to protect the Proton until ground wind velocity exceeds 20 meters per second, or more than 45 miles per hour. We have some footage of the mobile service tower and of the Proton's rollout and erection on the pad, which we'd like to show you now. Here we see the Proton with the Astra 1F spacecraft already encapsulated in the payload fairing and mounted on the launch vehicle, as it leaves the launch vehicle integration building 5 days ago. Rollout occurred at 6:30 a.m. local time on April 4th. From the integration building, the Proton traveled approximately 6 kilometers by rail to the launch pad. For this early morning transfer, Proton's payload fairing was covered by an insulating shroud to maintain the temperature range required for the Astra 1F spacecraft. In this sequence, we see the Proton being erected onto the pad itself. The Proton is erected while still attached to its rail transporter. The entire operation takes about 15 minutes. In this shot, we see General Vladimir Ivanov, head of the Russian Space Forces, and Mr. Anatoly Kiselev, Director General of Khrunichev, leaving the pad after a personal inspection of the vehicle. Here, the mobile service tower approaches the Proton after the completion of preliminary checks of Astra's RF systems. The MST's work platforms close around the Proton to provide access to critical launch vehicle systems and to the spacecraft. This is Proton launch control at T-minus 19 minutes and counting. Launch constraints are those mission rules that govern the go, no-go decision to launch. Such rules apply to the Proton just as they do to any other launch vehicle. But for Proton, such constraints are less severe than they are for most other launchers. In particular, the weather has relatively little impact on Proton operations. Proton can lift off safely within a temperature range of minus 45 C to plus 45 C. That's about minus 50 degrees Fahrenheit to plus 120 degrees Fahrenheit. As already mentioned, Proton can lift off into ground winds as high as 16.5 meters per second, and upper atmosphere winds here at Baikonour almost never exceed those for which the Proton was designed. Lightning is an occasional concern in this part of the world. Proton won't lift off if any lightning is detected within 10 nautical miles of the launch site or planned flight path, and of course it won't be allowed to fly into thunderstorms or extremely heavy cloud layers. Weather is not likely to be a problem for us tonight as we approach the T-minus 18-minute mark in the count. The launch window for this morning's mission is 10 minutes long, which is considerably shorter than the 1 hour or so that one would usually encounter when launching a spacecraft such as Astra on another launcher. The reason for this is the fact that the Proton does not perform right ascension of ascending node steering, so the time of launch is rigidly determined by the allowable errors in the accuracy of orbit insertion. Even so, most Proton launch delays have been the result of payload problems. The Proton itself has rarely missed a launch window. If for some reason the launch cannot be accomplished this morning, another 10-minute window will open at 5:10 a.m. tomorrow. Astra 1F will become the sixth member of a constellation of co-located satellites, the first 5 of which consist of Astra 1A, launched on December 11, 1988, Astra 1B, launched March 2, 1991, Astra 1C, launched May 12, 1993, Astra 1D, launched November 1, 1994, and Astra 1E, launched on October 19, 1995. The Astra 1F satellite, manufactured by Hughes Space and Communications Company, is an HS-601 3-axis stabilized model. It is cubical in shape and composed of 2 modules. The primary structure, called the bus module, contains the spacecraft's propulsion system, electronics, and battery packs. The payload module is that portion of the satellite that makes up the actual communications equipment and solar panels. Astra 1F's communications payload consists of 20 active channel amplifiers in the Ku band. Astra 1F weighs 3,000 kilograms at launch. The solar arrays measure nearly 26 meters across, and the antenna is more than 7 meters when fully deployed. Astra will be launched in a stowed configuration and deploy its communications reflectors, telemetry and command antenna, and solar panels following separation from the launch vehicle. Once on orbit, Astra 1F will uplink television and radio channels from several cities in Europe and broadcast the signals back to cable networks, blocks of apartments, and individual homes across Europe. We now have a short video describing the Astra spacecraft and the operations of SES in further detail.
SES, Société Européenne des Satellites, is the operating company of Astra. Astra, a satellite system designed for analog as well as digital distribution of television and radio programs throughout Europe. Created in March 1985 and based in Luxembourg, SES is Europe's first private satellite operator. The company operates under a franchise agreement with the Grand Duchy. SES's headquarters are located at the Château de Betzdorf, a former residence of the Grand Duke of Luxembourg. The company employs over 180 staff from some 15 different nations. Next to the administrative building are located the Astra ground control facilities with the large parabolic antennas which are used to control and steer the satellites in space, as well as to transmit video, audio and data signals to the satellites. A separate antenna is used for each of the Astra satellites. The Betzdorf site also comprises various communications antennas for the reception and transmission of TV and radio signals. Société Européenne des Satellites has several subsidiaries in Europe. In Germany, in Frankfurt. In the UK, in London. In France, in Paris. In Spain, in Madrid. The 8 satellites in the Astra system, of which 5 are already in operation, feature reliable technology as well as advanced satellite design. Every satellite is constructed individually, and it takes highly qualified specialists about 3 years to build an Astra satellite weighing approximately 3 tons. The satellite is very sensitive and needs to be assembled in a completely dust-free environment. Each part undergoes rigorous testing to ensure that it functions perfectly on its own and as a part of the system. Precision testing at ground level ensures that the satellite will perform perfectly in space. Television and radio operators broadcasting via Astra transmit their programs to uplink stations at the locations shown here. The signals are then sent from these uplink stations directly to the Astra satellites. The uplink is carried out via antennas like the ones shown here in Betzdorf. The fixed antennas on the ground see the satellites as a single fixed point in the sky. So when the picture arrives on your screen, it has already traveled 72,000 kilometers at the speed of light. On June the 7th, 1988, Sky Television announced its decision to take 4 transponders and became Astra's first client. Today, the Astra satellite system offers you a wide choice of analog as well as digital television, by country, by language and by special interest, be it general entertainment or thematic channels, subscription services or programs transmitted in the clear. Additional audio subcarriers enable each television channel to carry different language soundtracks simultaneously and to carry analog as well as digital radio channels. Astra offers alternative television, radio and other new services for everyone. The Astra system has been designed for the future requirements of TV viewers all across Europe. The satellites currently in operation and those already under construction will ensure the continuation of this system well into the next century. Whatever technology comes along, Astra is ready and waiting. By co-locating additional satellites at the same orbital position of 19.2 degrees east and by using digital compression technologies, Astra is able to offer an unrivaled number of television and radio programs, all available on a single fixed antenna. Astra offers freedom of choice. Astra, Europe's satellite system.
During this morning's launch, the first 3 stages of the Proton will follow a standard ascent trajectory to place the 4th stage and the Astra vanaf spacecraft into a 200-kilometer circular parking orbit inclined at 51.6 degrees to the equator. Once in parking orbit, Astra will be propelled to its transfer orbit by the Block DM upper stage. The targeted parameters of the transfer orbit include a perigee altitude of 12,100 kilometers, an apogee altitude of 36,000 kilometers, and an inclination of 7 degrees. Once in transfer orbit, the Astra vanaf spacecraft will separate from the Block DM at a mission elapsed time of 6 hours, 41 minutes, and 10 seconds. Astra will then deploy its antenna and solar arrays and conduct checkout operations for several days before igniting its own onboard liquid apogee engine to place the satellite into its final geosynchronous orbit. Just a few minutes ago, the Astra vanaf spacecraft manager signaled Astra's readiness for launch. At T-minus 5 minutes, the Proton's first 3 stages will give their okay to launch. And at T-minus 1 minute and 53 seconds, the Block DM upper stage will give the final go for launch. The engine start command will be given by the automatic sequencer at T-minus 2.5 seconds. Let's listen for announcements from the firing room as we enter the final moments before launch. This is Proton Launch Control at T-minus 8 minutes and counting. In just a moment, we'll be coming up on T-minus 5 minutes and counting. T-minus 5. T-minus 4 minutes and counting. T-minus 3 minutes. T-minus 2 minutes and counting. T-minus 1 minute and counting. 5 seconds. Engine start. Liftoff. We have liftoff of the Proton on its first commercial mission, carrying the Astra vanaf spacecraft into geosynchronous orbit.
Полет нормальный. Параметры траектории полета ракеты-носителя соответствуют расчету. 110 секунд. Давление в камерах сгорания двигателей в норме. 120 секунд. Измерительные средства космодрома ведут прием и обработку информации. Прошло отделение...
Stage 1 separation complete.
Запуск двигателей второй ступени. Двигатели второй ступени вышли на режим. 140 секунд. Стабилизация устойчивая. Давление в камерах сгорания в норме. 150 секунд. Система управления работает нормально. 160 секунд. Полет нормальный. Телеметрические средства космодрома ведут прием и обработку информации. 170 секунд. Тангаж, рыскание, вращение в норме. 180 секунд. Полет нормальный. Параметры траектории полета ракеты-носителя близки к расчетным. 190 секунд. Стабилизация устойчивая. Давление в двигателях в норме. 200 секунд. Полет нормальный. Траектория близка к расчетной. 210 секунд. Тангаж, рыскание, вращение в норме. 220 секунд. Давление в камерах сгорания устойчивое. 230 секунд. Полет проходит по программе. 240 секунд. Стабилизация ракеты-носителя устойчивая. Наземные измерительные средства космодрома ведут прием информации. 250 секунд. Полет нормальный. Все системы тут сканируют нормально. 260 секунд. Параметры траектории полета ракеты-носителя близки к расчетным. 270 секунд. Давление в камерах сгорания двигателей в норме. 271 280 секунд. Стабилизация ракеты-носителя устойчивая. Параметры системы управления в норме.